centuries the exclusive domain of cactus and rattlesnakes. Today, in the middle of the Mojave, rests the ultimate boom town, Las Vegas. The destruction of a hotel like the Sands is a rite of passage in Las Vegas. Here, on a regular basis, a smaller, older building will come down in a cloud of dust to make way for a larger one. 3 years and $1.5 billion later, the Venetian Hotel opened where the Sands once stood. The Venetian, which is the size of 104 football fields, is just one of dozens of towering buildings that have turned this patch of desert into the ultimate gambling oasis. But none of this would exist without heating and air conditioning.
There are few ideas in history that have had such a great overall impact on the world and the way that we do things and the way that we live.
And living in Las Vegas means keeping cool in a city where outdoor temperatures often top 110 degrees. But thanks to heating and air conditioning, you can bet the temperature inside the Venetian will always remain a comfortable 70 degrees. Surprisingly, the process for cooling begins outside in the scorching desert heat. High-powered fans like these, stationed around the Venetian, draw hot air inside. What will turn this hot air cold are 10 massive 2,000-ton machines called chillers. They are housed inside the casino's mini processing plant, nicknamed the heart of the house.
A chiller is kind of the reverse of a boiler. If you think of a boiler that heats up and makes hot water to distribute around, the chiller makes cold water to distribute around. That cold water is usually somewhere in the neighborhood of 40 to 45 degrees.
The key to keeping the water cold are refrigeration chemicals. Like most modern-day systems, the one at the Venetian uses an environmentally friendly chemical called 134A, which is replacing Freon and other ozone-damaging chlorofluorocarbons.
That family of compounds would gradually migrate up to the upper levels of the atmosphere and reduce the amount of ozone in the upper atmosphere. The ozone is something that does help shield us from ultraviolet radiation from the sun.
Refrigeration chemicals easily change from a liquid to a gas and back to a liquid. And in the process of changing from a liquid to a gas, they absorb a tremendous amount of heat. That heat comes from water in close proximity to the refrigeration pipes inside the chillers. The result is colder water. That cold water is then piped to a network of coils housed inside air intake units. Cooled water chills these coils.
Air is blown across that water coil with a fan and then back to the chiller. The air is then sent down the ductwork after it's been filtered, and that air is delivered to the rooms through the ceiling.
Ensuring that more than 60,000 guests each day can gamble in climate-controlled comfort. When it's cold outside, the same process is used for heating the building. Only boilers do the work of chillers. A boiler is a large steel drum that contains water. A natural gas unit provides the fire that heats the water to well over 200 degrees. This hot water produces steam that is pumped through the pipes to the coils that warm the incoming air. Technology has allowed us to control our indoor environment. But with all its modern-day sophistication, the roots of heating and air conditioning date back to two of Earth's ancient elements: fire and ice. Campfires were the earliest and only heating systems for thousands of years.
The evolution proceeded from a simple campfire out in the open to the idea of bringing the campfire inside.
Fire warmed caves and huts for centuries. Around 2500 BC, the hearth was used by the Greeks to heat rooms. And about 1,000 years later, the Egyptians introduced the bellows to fan the flames and enhance the heat of fires. But central heating remained elusive until around 100 BC, with the rise of the Roman Empire and their hypocaust system. The first central heating system ever developed, it required that homes and buildings be constructed with raised floors that rested on sturdy ceramic tile pillars. The shallow basements created by these raised floors were connected to furnaces where wood was burned. During the next few centuries, Romans continued to improve the hypocaust heating system, modifying it so that the wood-burning furnace was outside the building. The heat from the furnace would rise through a metal pipe connected from the furnace to the building.
They got to the point where they brought the hot air and flue gases of the fire underneath the floor of the building and actually up through the walls themselves. So you would have not only a heated floor, but you also had heated walls as well.
The buildings were made of stone, which is very good at retaining heat. But despite the hypocaust system's effectiveness, the concept of heating an entire structure from one source was forgotten with the fall of the Roman Empire. For many centuries, heating returned to building campfires indoors. Only this time, the campfires were housed inside a structure known as a fireplace. Wood was still used as fuel. Families had to huddle close to the fireplace to enjoy its warmth, as much of the heat went right up the chimney with the smoke. In the 1400s, the Germans came up with a better solution: the metal heating stove. Using wood as fuel, it radiated heat in all directions.
You could actually contain the fire totally inside the stove, so you had a much more efficient and controllable means of heating with a stove than you did with a fireplace.
Despite their popularity, stoves could only heat one room. It would take a revolution to change all that, the Industrial Revolution.
As we hit the Industrial Revolution, that's really what gave a kick in the pants to the idea of really developing true central heating systems as we now know them.
In the early 1800s, American inventor Daniel Pettibone examined diagrams of the ruins of the Roman Empire and discovered their sophisticated hypocaust heating systems. Inspired by the Roman system, Pettibone designed one of the first successful modern-day central heating systems. He built a brick chamber with a stove inside. Cold air entered the chamber at the bottom, was heated by the stove, and this warm air rose through ducts in the walls of the rooms. The system, which was installed at Pennsylvania Hospital in Philadelphia, relied on heat naturally rising. So there was no consistency in temperature from one room to the next. Engineers solved that problem using two new inventions.
You were able to take a mechanical fan, power that with a steam engine, and then use that air to ventilate and heat a building.
Forced air heat had arrived. The source was a stove or furnace, and the fuel was either wood or coal, which came into widespread use in America with the opening of the first commercial coal mines during the 1740s. Throughout the first half of the 19th century, the demand for central heating grew, first in industry, then homes. A key component in this heating system was a boiler, which worked on the same principle as those at the Venetian. A boiler in the basement heated water, which rose through pipes either in the form of hot water or steam, depending on the design of the system. The pipes were connected to a radiator in each room. The radiator was a large iron structure with cavities through which hot water or steam would circulate. The steam or hot water warmed the iron radiator, producing heat. By the early 1900s, radiators became the rage.
We had radiators that could go around columns of buildings. We had radiators that could go in corners. We had stair-step radiators that you could put under the stairs. We even had radiators with warming compartments in them with ornate doors that could be put in the dining room. And so you could put your food in these things and keep it warm while you were having your first course of your meal.
Regardless of what system people chose to install, they all shared a common problem. Much of the heat was escaping from the building.
The law of thermodynamics says that heat always moves in a direction from warmer to colder. In the wintertime, you have the condition of colder outside, so the heat that's in can go out very easily.
To keep the heat indoors, engineers developed insulation. Early attempts included corn husks, sawdust, and pine cones. In the late 1800s, people ground up old newspapers, treated it with fire retardant, and stuffed it in the walls. Unfortunately, these early insulators attracted unwelcome house guests. Rodents. Finally, in the early 1930s, engineers found a way to take compact strands of tiny glass fibers, melt them, spin them like cotton candy, and create fiberglass insulation, today's standard.
Insulation is very important when creating a system. Remember, heat naturally flows in the direction from hot to cold. The more insulation you have, the slower it is for anything to get through.
Another insulation gained popularity in the early 1900s. Asbestos. Asbestos is a mineral comprised of microscopic fire-retardant fibers. It's very effective for holding in heat. But if these particles should break away from the insulation and become airborne, they can embed in a person's lungs. Asbestos can cause cancer. It stopped being used in the 1970s and 1980s. Insulation helped contain heat, but maintaining a consistent room temperature had always been a problem. Coal was the primary fuel, and the only way to get coal into a furnace was to shovel it, which meant somebody had to be around day or night to stoke the coals when the fire died down. That changed with electricity.
Once we had electric power, then we could use a thermostat to actually control an electric current to turn an electric motor off and on.
The thermostat became an integral part of central heating. Mounted on a wall, it was connected by wires to a motor attached to the furnace. As the temperature dropped inside a house, it sent out an electrical signal to the motor to start the furnace. Along with electricity and thermostats came new fuels, oil and natural gas. This combination ignited the development of central heating and forever vanquished the bite of winter. Next, the remarkable discoveries that led to controlling the weather indoors during the dog days of summer. For centuries, this was one of the few escapes from summer heat. And if you didn't live near water, you found the nearest shady spot. The technology of keeping cool lagged far behind that of staying warm. In ancient Egypt, fans were used by servants to cool their royal masters. Many cultures developed fans that could fit in a person's hand, but they didn't provide much relief. Keeping the masses cool didn't become a real concern until the rise of factories. During the summer, many of them were like sweatboxes, devastating to workers and economically disastrous to many of the products being made.
In candy manufacturing, if there was too much humidity in the factory, the candy or the chocolates would stick together and the yarns and the wools would expand and contract, and it was very hard from one day to the next to have any kind of consistency in the product.
These businesses desperately needed a lifeline to survive. It came first in the form of ice. Ice as an industry flourished in the summer.
A gentleman by the name of Frederick Tudor decided that he could make money by actually harvesting ice, storing it, and selling it in warmer parts of either the United States or in even some other countries.
Harvesting ice became big business. Every pond, lake, and river that froze over during the winter fed this growing industry. Ice houses, some looking like crude warehouses, others resembling palaces, were built to store the millions of tons of ice being harvested each winter.
Usually they would use things like sawdust or straw in between the blocks of ice so that they wouldn't stick together. You could store ice for an entire season all the way through the summertime. The
public developed an insatiable appetite for ice. It was used primarily to preserve food. But an assassin's bullet would create a new demand for ice. On July 2, 1881, President James Garfield was mortally wounded by a gunman. Doctors feared the oppressive heat would destroy any hope of saving his life. They searched for a way to cool his room. Navy engineers assembled an ingenious device using fans and ice. A giant fan sucked hot air from the outdoors. Overhead was a cistern filled with shaved ice and water. A pipe carried that cool, melting water to a case containing 36 terry cloth rollers. The warm air from outdoors blew across these cold, water-soaked rollers, creating chilled air that fed into the president's room.
It was a very simple system, but it happened to work very well for the purposes. Unfortunately, the president did die of complications from being shot.
In his death was born a dream of mass marketing room cooling machines. That is, if engineers could find an alternative to the 4 tons of ice needed each day to operate a cooling device like the one used by the president.
You have to remember that early on we didn't have electricity, we didn't have an easy way to be able to produce a mechanical effect. For that reason, the first comfort cooling that really was applied was mostly to larger buildings, where we would use a steam engine to drive a fan, use that fan then to blow air over blocks of ice and distribute that within a building itself. Certainly, we couldn't put a large steam-driven fan behind a big pile of ice, for somebody's house.
The breakthrough came with the discovery of creating ice artificially, using mechanical refrigeration. Engineers found that chemicals such as methyl chloride and ammonia had cooling properties, which could be used to lower water temperature. Sealed containers were assembled for holding water. Compressors powered by steam engines were hooked up to pipes running into the containers. The refrigeration chemicals were piped into these containers and worked in much the same way as current refrigeration chemicals, to lower temperatures below freezing and turn water into ice.
Unlike melting ice from a pond, you don't have any of the scum or any of the impurities. This was nice and clean.
This same technology used for making ice was applied to cooling rooms. And in 1901, engineer Alfred Wolff designed one of the first mechanical room refrigeration systems for the New York Stock Exchange. The refrigerant of choice was ammonia. It was pumped through pipes that cooled the water inside 3 100-ton chillers. The cool air was released through 42 vents hidden inside the ornate ceiling of the stock exchange. And the warm air was vented outside through ducts. The system worked well, but there were flaws. The cooled air being fed onto the trading floor was not at a consistent temperature. Moreover, the level of humidity inside the stock exchange fluctuated.
We're all familiar with the phrase, it's not the heat, it's the humidity. To be able to take humidity out of the room is really the thing that makes us much more comfortable on those hot and muggy days.
Humidity is measured by how much moisture 1 cubic foot of air can hold. As temperature is lowered, moisture condenses out of the air. So at 92 degrees, a cubic foot of air can hold 16 grains of water. But at 31 degrees, it can hold only 2 grains of water. The inspiration for solving the humidity problem came to Willis Carrier in an uncanny manner, when in 1902, the young engineer was waiting for a train.
While waiting for his train on the platform, fog rolled in. And it was during this time where this dense fog came in that he had a flash of genius.
In that moment, Carrier realized that the key to controlling humidity in a room was to be able to replicate fog-like conditions inside a mechanical refrigeration system. Since the source of air used for cooling a building comes from the outdoors, the temperature fluctuates, and so does its humidity. Carrier designed a machine that had tiny water sprays in it, so as the outside air was drawn in, it would be saturated with water at a temperature where it could hold 100% humidity. Since that saturated air would now have a fixed amount of humidity in it, applying principles of physics, when it was cooled by the system and released into the building, it would always contain a precise amount of humidity. When that air mixed back into the warm, humid air of the building, it effectively cooled and lowered the humidity of the building's air. He called his device the apparatus for treating air. It was patented in 1906 and became the forerunner of modern-day air conditioning systems.
The apparatus for treating air was well received, particularly in industries where humidity was a big factor in manufacturing.
Known as the father of air conditioning, Carrier set up his own company in 1907 and mass-produced systems for everything from factories to hotels. However, most Americans could only experience the comforts of air conditioning at the movies. Throughout the early 1900s, many movie theaters closed in the summer months. That all changed in 1917, when the Central Park Theater in Chicago became the first fully air-conditioned theater. Others followed, and by the early 1920s, Americans were rushing to the movies. For many years, air conditioning and heating were two distinctly separate units. They were eventually combined to share the same thermostat, coils, and ducts. Next, from impossible dream to luxury to necessity, heating and air conditioning changes the entire face of America. By the late 1920s and early 1930s, air conditioning had come into the American home. Freon replaced methyl chloride and ammonia, which were found to be highly toxic if they leaked out. Early home air conditioners were huge room units modeled after refrigerators.
You probably felt the heat coming out of the back of the refrigerator or from underneath. What we do is we take heat in a refrigerator out of the inside of the box and we move the heat to the outside. It wasn't too much of a leap to take that type of a system and say, okay, we can not only cool an icebox with that, but we also can take that and actually cool a room.
Some of the early air conditioners were on wheels and could be moved from room to room. The warm air was vented out the window through tubes. These portable systems were later replaced with a fixed window unit that's still popular today. Air conditioning was marketed as an essential component of modern living. Manufacturers claimed it promoted better sleeping and eating and healthier dust-free homes. Americans bought the pitch and became a nation of air conditioning addicts.
Cool your entire home with Trane central air conditioning. It can be installed.
In the early 1950s, central air conditioning first appeared in homes, and with it, architecture forever changed. Before air conditioning, homes were designed to stay as cool as possible, using overhanging eaves for shade, opposing windows for cross-ventilation, and porches, which provided refuge from the heat of a home on a summer day. When central air conditioning came into the home, these architectural cooling devices slowly vanished. But air conditioning did more than just change the home.
Probably the bigger thing that air conditioning really did was allow you to start building and have a lot of expansion in areas where it's a lot warmer. Air conditioning really is the thing that created the entire business structure that exists in the South.
And with business came people.
It affected the migration of the U.S. population, changing it from the south to the north to the south.
Air conditioning fueled the growth of America's Sun Belt. It became cool to live in places like Las Vegas, Atlanta, Miami, Phoenix, and Houston.
They all existed before air conditioning, but they were outposts. They weren't the big population centers and the big business centers that we think of today.
As business centers shifted and grew, so did the design of the buildings people worked in. The office buildings of an earlier time were decidedly uncool. During the 1800s and early 1900s, they stood only a few stories high. They often featured spacious courtyards and windows that opened to try to enhance air circulation. Many buildings were decked out in awnings from top to bottom in an attempt to provide shade. During the winter, heat was provided by large boilers and furnaces in the basement. But in the summer, working in an office building was a test of endurance.
If you are working and all you're doing is sweating in an office building, it really hurts people's productivity.
Not to mention morale.
As the day progressed, it would become hotter and hotter inside. The humidity would be rising. Pretty soon you were sticking to your desk. Yes, you had your handy table fan sitting there blowing air over you, but it wasn't doing much good.
Central air conditioning came to the rescue in the late 1920s.
The essential impact on high-rise buildings is that it allowed us to enclose the building. We no longer were dependent on open windows for ventilation.
In fact, high-rises became towers of glass. One of the first to be erected was the United Nations building, built in 1952.
We could design a building with lots of windows in it because we didn't have to worry so much about how much heating would occur in the summertime, and we didn't have to worry about how much cooling effect we would have in the wintertime from all of those windows. We no longer had to rely on secondary things such as awnings to shield a window from the sun coming in and making the room extremely hot.
Air conditioning made it possible to work longer hours in summer and helped increase productivity. It's one thing to create man-made weather for a stationary structure. But next, how would engineers heat and air condition the fast-moving world of planes and automobiles? When cars were invented during the late 1800s, absolutely no thought was given to climate control.
When it was hot, they'd be hot. When it was cold, they'd be cold. But that's what motoring was about back in those days.
Their open-air design made them totally impractical in bad weather.
Automobiles did not find extensive use during winter months. Around Thanksgiving time, people used to take their automobiles off the road, put it on the cinder blocks and store away for winter months. And we would bring out the automobiles again in springtime.
Those that did brave the weather sought protection from the elements underneath a huge rubberized cloth called a storm apron. Around 1908, closed-body cars were introduced. So were some strange ways of heating them. Drivers and passengers warmed stones in their home fireplace, wrapped them in cloth, and kept them on their laps. The alternatives were not much better.
Some tried to take the heat of the engine's exhaust and route it into the passenger compartment. Not a very good idea, what with exhaust being the pollutants they are.
Not to mention how toxic those fumes are.
In the early days of motoring, several deaths occurred. So in response to this concern, heater engineers developed what are called the hot water heaters.
Introduced in 1926, the hot water heater was mounted under the dashboard. The heat of the engine warmed water that passed through a maze of small tubes just behind a fan that circulated the warm air through the car. These hot water heaters were extremely effective and extremely popular. In fact, nothing changed for 10 years, until 1937, when auto manufacturer Nash stirred excitement with what would become the model for all other car heaters.
Just a twirl of the dial of the weather eye control transforms January into June.
The weather eye operated in much the same way as a home heating system, drawing fresh outside air into the engine compartment, where it was heated by the engine, filtered, and released inside the car. There was a price to pay for this newfound level of comfort. For years, heating was a high-ticket luxury item.
During the 50s and even into the 60s, heaters were likely to be an extra cost option. By the 70s, heaters were pretty much a standard feature. Not air conditioning.
For decades, cooling a car was of far less concern than heating it. cars were open top and provided fresh air. And even after cars were enclosed, people seemed happy to just roll down a window and catch a breeze.
We used to have what we called 440 air conditioning. 4 windows down, 40 miles an hour. And that's what people drove around with for years and years and years.
There were a few attempts at comfort cooling. Some manufacturers installed vents. But this brought in more dirt and dust than it did cool air. In 1930, John Hammond Jr., a wealthy Texan who suffered from severe hay fever, paid the Kelvinator Refrigerator Company $1,000 to mount a special cooling device on the back of his Cadillac. Although too bulky and expensive for the mass market, it nevertheless marked the first time an air conditioning system appeared in a car. Soon after, auto manufacturers raced to see who could be the first to develop a fully air-conditioned car. The winner could reap millions in sales. On November 14, 1939, at the Chicago Auto Show, Packard Motor Company surprised the industry by exhibiting the first air-conditioned car. The AC unit used Freon as a refrigerant, which worked much the same way as home units.
This created quite a sensation, and especially people from the Southwest, they wanted to have this system installed into their automobiles at the earliest.
Sales of Packard soared. It wasn't long before other auto manufacturers rolled out their own air-conditioned cars. They all had one thing in common. The air conditioning unit was mounted in the trunk. As the technology advanced, the key components got smaller. And finally, in 1954, Pontiac introduced the first air conditioning unit small enough to fit under the hood. And the entire auto industry adopted it as the standard system. But as Americans began commuting in their air-conditioned cars, a new form of transportation was starting to change the way people traveled. The airplane.
It was faster than ground transportation, but still nothing like it is today.
What slowed the speed and development of commercial flights was the lack of breathable air at high elevations.
Traveling above 8,000 to 10,000 feet would put you in an environment that is really unsafe. The air would be too thin. The air is typically not breathable. They can become dizzy or faint.
Cabins weren't pressurized, so strict elevation restrictions existed for passenger safety. Cabins were kept cool by allowing air from outside to enter through vents.
It's like just opening a damper in your car and having air blow in.
Heating wasn't much better.
There were crude methods of heating, usually using either combustion heaters where additional airplane fuel was burned and fresh air passed over it, or taking exhaust air from the engine, which is typically hot, and again passing fresh air over it.
Then on July 8, 1940, TWA introduced the Boeing 307 Stratoliner, the first commercial plane to provide pressurized air-conditioned cabins. It was a system that translated well into today's jets. What makes it unique from air conditioning systems on the ground is that refrigerants are not used. Instead, a combination of outside air and the plane's engines heat, cool, and pressurize the cabin.
The way a gas turbine engine works is air is drawn in, it's compressed, then it goes through a combustor where fuel is added and the energy level is increased, and then it's expanded through a turbine. So if you go to that point of the cycle, you have compressed air, but it's still fresh air because the fuel hasn't been introduced yet. The compressed air is taken off of the engine through a little hole in the side of the engine. So you get the compressed air you need to pressurize the cabin.
That same compressed air is also used to heat and cool the plane.
The outside temperature at 35,000 feet is approximately minus 40 degrees Fahrenheit. The temperature of the compressed air coming out of the engine probably runs around 500 degrees Fahrenheit. So you take the 500 degree air and you pass minus 40 degree air over it in a heat exchanger, which cools it down to the proper temperature that you're looking for.
The air being fed into the cabin through overhead vents is a mixture of 50% clean processed air from the outside and 50% recirculated air from inside the cabin that has been passed through high-efficiency HEPA filters, similar to those used in hospitals. Thanks to climate control, yesterday's fantasy of visiting faraway places is today's routine journey. Next, heating and air conditioning take us to the world of tomorrow's fantasies. You are looking at one of the cleanest places on Earth. It is here that a tiny electronic component is manufactured that transformed the world. The computer chip. And what made the chip possible is a place called a clean room.
We'd still be living in the 1940s if it weren't for clean room technology.
But clean rooms would not exist without heating and air conditioning. Heating and air conditioning units were combined with high-efficiency filters capable of removing contaminants 200 times smaller than the cross-section of a human hair to create these super sterile environments.
In a clean room, the entire ceiling is a large air delivery system. It's maybe 95% covered by high-efficiency filters through which large amounts of air are blown.
In addition to high-efficiency filters, what makes clean rooms clean is the speed at which the cooled air can be recirculated.
That's accomplished by large air conditioning systems, very high-efficiency fans, and the laminar flow technology that allows the air to flow directly from the ceiling to the floor at relatively high velocities.
Unlike a standard air conditioning system that vents air horizontally, the laminar flow drives air downward in a vertical direction. The floor of a clean room is covered with giant grates, allowing air to circulate swiftly through the room.
In a standard home air conditioning system, you might have 2 air changes per day, meaning that the volume of air in the home is completely replaced twice per day. In a microchip manufacturing fab, you would have up to 6 air changes every minute, meaning that the entire volume of air in the whole room is changed every 10 seconds.
Clean rooms were first built in the 1950s for the aerospace and defense industries to manufacture contamination-sensitive parts for guided missiles. Today, they're used for everything from making computer chips to developing life-saving drugs. Heating and air conditioning led to new discoveries on Earth and made it possible to conquer space. Astronauts could not survive in this deadly environment without their air-conditioned spacesuits.
For starters, there's no air to breathe. In addition, we deal with a large range of temperature extremes, from minus 250 to plus 250 degrees Fahrenheit, and there's no gravity.
Engineers solved the problem of staying warm by designing the suit with multiple layers of insulation. But the spacesuit is so well insulated that the heat given off by an astronaut's body inside the 250-pound garment makes it unbearable to wear. So, like the massive chillers and pipes that pump cold water through an air-conditioned building, engineers designed a mini-chiller system, known as a liquid cooling and ventilation garment.
That garment contains about 300 feet of plastic tubing woven in and around a layer of fabric that's close to the astronaut's body. Within the cooling garment, liquid water is flowing through the tubes. And in the same fashion, when you pick up a garden hose and your hand feels cool because the water's flowing through the hose, what's actually happening is that the heat is moving from your hand into the hose. By the same fashion, the heat moves from the astronaut's body into the liquid cooling garment.
The warmed water is carried to the primary life support pack on the astronaut's back. A device known as a sublimator helps recool the water, and the heat pulled from the water is vented into space. The recooled water is then pumped back to the ventilation garment. There's even a thermostat, so the astronaut can adjust the temperature inside the spacesuit.
An astronaut is really walking around with his own self-contained heating and air conditioning system.
Heating and air conditioning may have changed our world, but they may have made us more vulnerable to the threat of terrorism. Heating and air conditioning systems circulate air through an entire building, making it an effective weapon for terrorists in spreading deadly viruses. Although merely sent through the mail, the 2001 anthrax attack on some government buildings in Washington, D.C. demonstrated our vulnerability. But engineers are fighting back, using ultra-high efficiency filters that can trap deadly viruses before the heated or cooled air is released into the ducts.
It'd be stuck at the filter and we could kill it there. We could put ultraviolet lights, which is a way of killing a lot of different kinds of substances, but not all.
Those viruses that can slip through today's filters will someday soon be trapped, thanks to a new generation of ultra-high efficiency filters being developed.
Anthrax spores would be captured by the ultra-high efficiency filters in a clean room, so they would be taken out and disposed of before they could endanger any personnel.
Safety may be a concern, but for most of us, our focus remains on comfort. And heating and air conditioning have provided an unimagined level of comfort. An enormous accomplishment, too easy to take for granted.
We have taken fire and we've taken ice and we've molded them in such a way that we have taken the idea of indoor environmental control from a concept that once was considered the realm of the gods, and it's almost like we have become gods in our own right, where we can actually control something that was considered to be uncontrollable before.